Okay, so welcome to everybody. So first, let me thank Massimo, Kristian, Filippo, Samriddhi for organizing this nice workshop. It's always a pleasure to come to visit Bangalore, even if even in a virtual way this time. So I will present some recent results obtained in collaboration with Massimo, with Stefano Musacchio and Alessandro Sozza, on a simple model for inertial particle in a very simple flow, which is the Kolmogorov flow. And I will present two kinds of results. One is at low Reynolds number. We study the stability of the Kolmogorov flow and how the presence of inertial particle affect the stabilities. And the second part, I will present some result at high Reynolds number in the case of a turbulent flow. So I don't need to motivate you. One is interested in the inertial particle for natural environment and for technological applications, and I can skip this talk. And also I don't need to remember you, there are here in the audience, there are people much more expert than me on inertial particle statistics. And so in the limit of relatively small particle, we can use the Maxwell-Rayleigh model. And the general point that I want to make is that inertial particles can detach from the streamlines, so they can eject from vortices, for example, and so they remain not homogeneous distributed, but they form a small-scale clustering and preferential concentration. These are snapshots of the distribution of inertial particle in the two-dimensional and three-dimensional flow taken from people present in this audience. Jeremy did a lot of work on this problem. But in all these cases, the particles are passive, so they are transported by the flow, but they do not have a feedback on the flow because the density is supposed to be very small. And when when the concentration of particles is not too small, they start to have an effect on the flow. So they modify. Inertial particles can modify the flow, and I don't want to. So there are a lot of studies, of course, in this problem. Just I want to make a general statement that the phenomenology is quite complicated and rich. For example, in the case of laminar pipe flow, it is an old work by Guazzelli group, experimental work. They can change the stability of the laminar pipe flow with a non-monotonic effect. So this is the critical Reynolds number as a function of mass loading, and you have a non-monotonic effect in the particle concentration and as a function of the Reynolds number on the particle concentration, you have a different flow regime studied both experimentally and numerically by several groups. So this is just one slide to motivate to show you that the situation is very complex. So you want to study this problem with general complex problem very simplified, with a very simplified model and a simplified flow. So the model is a simple Eulerian model, so it's not exactly Lagrangian for particle in flow. The idea of the model is to consider a monodisperse suspension of a small particle, which you can neglect volume fraction. So we can neglect particle-particle interaction essentially, but the particles are heavy. So the mass loading is not negligible, can be of order 1. Think, for example, of water in air. The particles are small, so we can assume that the most important interaction with the velocity field is the Stokes drag. So we consider only the Stokes drag, and from the conservation of total momentum, you can derive this model, which is the Navier-Stokes equation, okay, with an external forcing which is needed to generate the flow, and there is this additional term which couple the fluid velocity with the particle velocity. So the idea is to introduce a particle velocity, which is transported by itself and is driven by the fluid velocity. So this is the coupling. And theta represents the number density field. So it's the particle concentration in terms of density field. And the other parameter, you have two parameters. This is the mass fraction phi, and tau is as usual is the Stokes time. So there are two dimensionless parameters. One is the mass fraction, the other is Stokes number, which is defined as the Stokes time normalized with some characteristic time in the flow. I will use, in the turbulent case, I will use the Kolmogorov time. So the model is pretty old, was derived by Safman 60 years ago, and it is not very well known. It's used in a community of people working in an astrophysical community, but not in turbulence community. Of course, the model in general is wrong, because we know that we cannot define in principle a Lagrangian velocity, because you can have a multi-value velocity for Lagrangian particle, for inertial particles, sorry, because they come from different point. But the idea is that the hope is that if the Stokes time is not too large, the Stokes number is not too large, we can neglect the fact that there are multi-value velocity, and we can try to see, we can hope that Lagrangian velocity for the particle, inertial particle, has a meaning. The advantage of this model is it's very simple, and will allow us to do some analytical prediction, at least in the case of laminar flow. So there is an important limit that I want to mention now, which was already discussed by Safman. If you take the limit of small tau, so tau is smaller than any characteristic time in the flow, you can expand the equation for the Lagrangian velocity. You can expand it at the first order in tau, is the usual expansion we have already seen in the inertial particle. And so at the leading order, the flow is incompressible. So we can assume that the density, particle density, is uniform. So this term here disappears. And so if you replace in the first equation this expression for V, we end up with a single equation, which is a Navier-Stokes equation, and if with a reduced viscosity and forcing. Okay? So what does it mean? It means that in general, if you consider now a flow at small Reynolds number in presence of particle, the presence of particle simply reduces the viscosity because increase the density. And so in general, we expect that at a fixed Reynolds number, the flow becomes more unstable. On the contrary, in the case of larger Reynolds number, in which the viscous term at large scale can be neglected, the effect of the presence of particles is generally to reduce the forcing. Okay, and this we will use these two limits in the following to understand what the result that we will obtain. Okay, so the flow that we use is a Kolmogorov forcing, so the forcing is sinusoidal, and we all know that this is a stationary solution, is the shear stationary solution of the Navier-Stokes equation, in which the amplitude is related by the forcing by this viscous link. And this was proposed by Kolmogorov for studying the transition to turbulence. And so let me remind very quickly that this laminar solution, the laminar Kolmogorov flow, becomes unstable to large-scale perturbation when the Reynolds number exceed a critical value, which is square root of 2. This is also 60 years old result, Belashki and Sinai. And when you increase the Reynolds number, the Kolmogorov flow becomes chaotic and eventually becomes turbulent. But what is here? Okay, this is an example of the Kolmogorov flow on this particular density field. But now, if you consider now the turbulent Kolmogorov flow, the remarkable property is that the mean velocity remains monochromatic. So the mean velocity has the same profile as the laminar profile. The Reynolds trace also in monochromatic, and so the momentum budget that you can write a stationary condition becomes simply an algebraic equation for the coefficient. And so if you introduce this, as usual, the friction coefficient, which is defined as the work done by the forcing over the kinetic energy, so F over U square, essentially. You have an expression for this friction coefficient, and numerical simulation done some years ago show that increasing the Reynolds number, the friction coefficient tends. So for low Reynolds number, you have the usual laminar 1 over Reynolds behavior, but for large Reynolds number, the friction coefficient tends to an asymptotic value, which is independent of Reynolds or with a weak dependency on Reynolds. This is still not clear, but we assume that it reaches an asymptotic value. Okay. Okay, so we want to, sorry, I skipped. Okay, this is the slide. So the first part of the talk, we discussed the effect of inertial particle on the laminar Kolmogorov flow. So I consider the Safran model. The forcing now is the Kolmogorov forcing. And the laminar solution is the same that in Navier-Stokes without particles. So the particle velocity is equal to the fluid velocity, is a monochromatic profile with uniform density. You can easily check that this is a solution of the Safran model. So we perturb this laminar solution. We use the standard machinery of multiple scale analysis to study the linear stability of this problem. So we study the linearized equation for the perturbation, and at the linear level, the density field becomes a passive scalar, so you can neglect the analysis. You have just the two velocity field, the fluid and the particle velocity. You expand in terms of multiple scales, so you introduce a large scale behavior capital X and a large time capital T. And then using the usual machinery of multiple scale analysis, you end with the solvability condition at which is at the end is an eddy viscosity equation for the perturbation of the velocity field U0. Okay, so it's an equation which you have one time derivative 2 times in space for U0 and the 4th time in space, so it's an eddy viscosity, and this defines the eddy viscosity as the ratio between the two coefficients, which is written here is a function of the Reynolds number of the flow, on the mass fraction, and on the Stokes number. So from this expression of the viscosity, you define the stability. The critical Reynolds number is the Reynolds number at which the eddy viscosity change sign becomes negative, which means instability. The expression is this simple one. Okay, so this is a generalization of the result of the square root 2 result for the usual Kolmogorov flow in Newtonian fluid. In the limit of the Newtonian limit, in which you have no mass fraction, so no particle, we recover square root of 2. And also I want to stress the fact that in the limit of very small particle, which the Stokes number goes to 0, the critical Reynolds number is simply the usual one rescaled by the factor 1 plus phi, which is exactly the rescaling of the viscosity. Okay, so you again, also in this specific case, we see that small particle destabilize the flow. But this is just one limit, and we have the full expression. So if you look at the stability diagram as a function of the parameter, which is the mass fraction and the Stokes number, you have something like this. So there are regions. So what I plot here is the critical Reynolds number normalized with the square root of 2. So the blue region are situations in which particles destabilize the flow, makes the flow more unstable with respect to the Newtonian case. And the red part is where it's more stable. So the critical Reynolds number is larger than the square root of 2. This black line is the neutral line, which is given by this expression. And in this line, the flow is equivalent to the Newtonian case. So you see that in general, the stability critical Reynolds number increase with the Stokes number, so going in vertical direction, so which means that Stokes makes the flow more stable, while the behavior in the mass loading is non-monotonic. And this is similar to what has been observed by Guazzelli in the pipe flow. So at the beginning, the flow is more stable. When Stokes is sufficiently large, you had that at small volume fraction, the flow is more stable, but then if you increase the volume fraction, at a certain point becomes more unstable with respect to the Newtonian case. So the picture also very simple model. We have a picture which is not, which is already some interesting features. So now I want to study the stability diagram in the vertical and horizontal cut, so as a function of Stokes and phi. And these are the result. The line represents exactly the prediction for as a function of Stokes number, for example, for different mass loading, or as a function of mass loading for different Stokes. Yes, Ganesh.
So I had a question. It's about, so I think you said that Stokes number needs to be smaller than some value of order unity, where there will be crossings, trajectory crossings, and the velocity will become multi-value. So there's some order 1 value, only below that value will the analysis be valid. Is that correct?
Okay, thank you for the question. Very nice. Yes, in general, for the general flow, yes, we cannot use Stokes of order 6 for this model to be valid. But remember, we are just studying here the linear stability of the flow in which the density is initially uniform. So we are looking if this flow with uniform distribution, so in this case, and the velocity at the beginning is the fluid velocity, so it's the single value velocity. We are studying if this configuration is unstable. So at the level of linear stability, there is no problem. Of course, we cannot extend the result to the nonlinear, weakly nonlinear or nonlinear phase. Okay, thank you very much for your question. In general, you're right, but for this specific problem, it's not a problem to use large Stokes number.
But the second question was also with regard to phi. You're using a dilute single particle picture, underlying picture, right? So what I was wanting to know was if, for instance, in the coefficient of V minus U in the drag term in the equation of motion, if you say that, let's say the drag coefficient has an order phi correction. So in that phi, you add a 1 plus phi or something like that, some mean field correction that accounts for interactions with other particles. In that last term in the first equation.
Yeah, I understand. So you are asking if I consider interaction among particles, can I rewrite in this term with a different coefficient? This is the question.
Yeah, I'm wondering if you add a correction of order phi squared to this equation, how will it affect your threshold criterion, stability criterion?
I have no idea. Depends how you make the correction. So the correction phi square, what does it mean?
Yeah, like
this is just a coefficient. Then you need the expression of the coupling term.
Correct. Yeah. So P plus C phi squared, something like that, by tau.
I have no idea. Really.
Okay. I mean, I'm just wondering if you're neglecting interactions. So what do you think about the range of validity of the volume fraction in your stability diagram?
Okay. So I neglecting many things, okay, because I neglecting also other terms. For example, if you consider the Lagrangian model, I neglecting, okay, I consider very heavy particles, so I neglecting gravity, this is okay, I neglecting other terms in the equation for the particles. So this is the first point. For what concerns your question, if I understood correctly, so I am assuming that the volume fraction remains small, but what is important here is the mass fraction. So if you have sufficiently large ratio between particle density and fluid density, you can have a mass fraction of order 1 with a volume fraction which is small, in which you can neglect particle-particle interaction. If you have a volume fraction, okay, then you have clustering, so the situation becomes more complicated. But if you assume a uniform distribution, if you have a volume fraction which is order 10 to the minus 3 or smaller, you can assume that particle-particle interaction is not very important.
Okay, thank you.
Thank you. So, okay, I was here. So what I plot here is the behavior of the critical Reynolds number as a function of Stokes and phi. And you see also points, and the points correspond to numerical simulation of the linear model, okay, the linearized model, that we compute the critical Reynolds number numerically. And so you see there is an agreement with a theoretical prediction, with an analytical prediction for not too large Stokes number, which depends on the mass loading, larger than 4 or 6, depending. And also we have deviation for intermediate value of the mass fraction. For very small mass fraction, we have a perfect agreement. If the Stokes number is not too large, we have a perfect agreement everywhere. But for larger Stokes number, larger than 4, we have a disagreement within the numerical prediction and the numerical result and analytical prediction for intermediate value or the mass loading. So the idea is to understand why it is happening. It is happening because of the breakdown of multiple scale analysis, in the sense that in these regions here, with the points, numerical points are different from the analytical prediction, the most unstable mode is not a large scale. And I can show you this single picture. This is what we compute numerically, the growth rate, okay, at the critical Reynolds number. So we fix at the given value of the parameter, we fix at the critical Reynolds number, and we compute the growth rate of the different modes. Kx represent the modes over the forcing mode. So the forcing mode is 1, is here. So these are large modes, large scale modes. And one of these modes is exactly equal to 0 because we are at the critical Reynolds number. So you see that for Stokes equal 4, if the volume fraction is very small, which are the red points, or very large, let's say, which are the blue points, the most unstable mode is the larger scale mode. So in this case, the assumption of scale separation between perturbation and basic flow is correct, is satisfied. So we may expect that the multiple scale analysis work, and indeed this is the case because we are here and here. But for intermediate value of the mass loading, which is this blue line, green line, which is phi equal 1, where the most unstable mode is of order of 0.3. In any case, is a finite scale, is a finite size modes. So in this case, the multiple scale assumption is not valid anymore, and so we have that we cannot be. So the stability cannot be captured from the analytical prediction. So it's not a surprise that for intermediate value of phi, the multiple scale analysis fails. Okay. So now let me move to the second part of the talk, the property of the turbulent flow. So now I consider the Kolmogorov flow at a large Reynolds number or moderate Reynolds number. The flow is turbulent. We don't have any analytical prediction in this case, so we use essentially numerical simulation. So we did a set of numerical simulation for different value of the parameters. So the Stokes time, the mass loading, at a given forcing, but the Reynolds number, of course, the Reynolds number changes because the property of the flow changing. So the main result that I want to show here is also that, first of all, the mean flow remains monochromatic, also in this case. This is not a priori, and even a posteriori is not very clear. I will discuss later in the talk why I'm a little bit surprised at the fact that the mean velocity field remains monochromatic, remains sinusoidal. So what I plot here is the mean velocity field average over time, average over plane as a function of zeta. There is still a sinusoidal profile. And what you see that increasing the mass loading, so the red line corresponds to the zero mass loading, so it's a Newtonian fluid, the particles are passive. Increasing the mass loading, we have a decrease of the mean amplitude of the velocity. So the mean velocity is reduced with the mass loading. This is more clear in this plot on the right, where I plot the amplitude of the mass of the mean flow as a function of mass loading. So this is a Newtonian case, and we have a monotonic increase in the concentration of particles. But what is more surprising that the three lines correspond to three different Stokes time. And so it seems that the effect of the particle increasing the Stokes time or the Stokes number, the effect of the particle is reduced. Okay, so particle with larger Stokes time, larger particle, if you want, gives at the given mass loading gives a smaller effect on the mean velocity. And we'll try to understand these two behaviors. So the first one, the behavior with phi, can be understood, at least in the limit of very small Stokes, can be understood by the Safman general argument that when you consider very small Stokes number, you remember that I stressed at the beginning that you can consider the flow as a Newtonian flow with a forcing which is reduced by the factor 1 plus phi. So because we are in a turbulent regime, we know from the picture that I showed before that the friction coefficient for the Kolmogorov flow is, which is given as usual at the forcing over u square, is almost constant, is constant. We assume that it's constant. So it means that the velocity, the mean velocity is proportional to the square root of the forcing. So because in this regime for small tau, the forcing is rescaled by a factor 1 or plus phi, it means that the mean velocity is expected to be rescaled by a factor 1 over square root 1 plus phi. And indeed, this is the dashed line represent this behavior that fits pretty well, or at least reasonably well, the points at the smallest Stokes time, the red points. Then the point now is to understand why this effect, the effect of particle, is reduced by increasing the Stokes number. And we'll try to explain that our interpretation that at least part of this result is due to the fact that the particles are not increasing the Stokes number, the particles are less and less homogeneous distributed. And so this makes a big difference in the feedback to the flow. Okay, so the particle, this is the particle distribution in the zeta direction in stationary condition for different mass loading. Okay, so the point is that in the Kolmogorov flow, also turbulent intensity is not uniform. The turbulent intensity is maximum in high shear regions, and is minimum at where the mean flow is maximum. Okay, where the shear is minimum. So it means that the particles are immersed in a turbulent flow which is not uniform, is not homogeneous, and so by turbophoretic effect, if you want, we expect the particle concentrate in region where the turbulence is lower. And the region where turbulence is lower are regions where the mean velocity is maximum. And indeed, the particle distribution, which is the average is 1, we are more particle, about 5–6% in this situation, more particle at the peaks of the mean velocity. Okay, which are here, here, and here. And we have a reduced concentration of particles in the region where there is the higher shear. And so this means that the region which are more turbulent, they see an effective number of particles which is reduced. Okay, and so this is the interpretation of the effect that of this effect, the fact that when you increase the Stokes number, okay, you are increasing the turbophoretic effect. Increasing this turbophoretic effect reduces the effective number of particles that you have in the high turbulent region, and so the effect is that at the end the effective mass introduced by the particle is reduced. Okay, so this is the result. To be more quantitative, let me consider now the momentum budget. So as in the usual Navier-Stokes, as in the Newtonian case, we have that the momentum budget becomes an algebraic expression because all the terms are monochromatic. We have an additional term here, which is an exchange term between the fluid velocity and the particle velocity. And so there are three different contributions. We can neglect the viscous contribution because at large scale is irrelevant because the viscosity is very small. So we have essentially two contributions. One is the Reynolds stress and the other is the Reynolds. Yes, the Reynolds stress, and the other the change term, which is 0, which is plotted here as the dashed line. It's 0 when you don't have mass loading, so all the forcing goes essentially in the Reynolds stress. But increasing the mass loading, we have an increase of this exchange term, which becomes of the same order of the Reynolds stress when the mass load is of order is equal to 1, which is the largest value that we have in our simulation. So this is an effect. This is an effect on the friction factor. The friction coefficient is defined as usual, as in a Newtonian case, as the forcing divided by the u square. But now we have an additional term, and so we expect that the presence of particle will affect also the friction coefficient, and so affect the drag, the turbulent drag of the Kolmogorov flow. And indeed, this is the case. So this is probably one of the last plots that I want to show you. And the black points represent the Newtonian case, okay, where the friction factor becomes almost independent of the Reynolds number. So there are different simulations at different Reynolds number. While these point here with color represent the simulation with the particles, with inertial particles, for different value of the mass fraction and Stokes number. The color represents the Stokes number. So you see that for zero mass fraction, of course, there is no effect on the flow. They stay together with an Hamiltonian case. But increasing the mass fraction, we have an increase of the friction coefficient. This increase depends, again, consistently what we have seen before, depends also on the Stokes time. It is reduced for larger Stokes time. But in any case, we observe that there is a drag enhancement. So the particle enhances the drag of the Kolmogorov flow because the friction is increased with respect to the Newtonian friction at the same Reynolds number. Okay, let me stress one point, which seems curious. All the points, because both F and Reynolds, so that the two axes do not depend explicitly in the definition by tau on tau and phi, all the points lie, the simulation lie, which are done at the same forcing, same viscosity, same scale of forcing scale, they lie on this line, okay, which is this line, which is plotted here as a dashed line. So all the points of the simulation lie on this line, so they can simply move along one direction. But they move, they go to higher value of the friction at a given Reynolds, so it means that there is a drag enhancement. And so the drag enhancement reduced the turbulence also. And so at the end, we have a kind of negative feedback on the turbophoresis because the presence of particle reduce the turbulent flow, reducing the turbulent flow, sorry, it reduces the turbophoresis, so that the density field with a plot here of the particle becomes more homogeneous, increases the mass loading. So there is a kind of negative feedback on the turbophoretic effect with respect to the passive particle, of course. And so this is the idea, is the end of my talk. I showed that how inertial particles affect laminar turbulent flow in the Kolmogorov flow. And if you want some more details, you can have a look to the two papers, that one for the laminar, the other for the turbulent case. But because I had a question before by Ganesh, let me show you just another, we have some time. Let me show another slide about the validity of the model with the Stokes number. So these are plots obtained some years ago in collaboration with Antonio Celani, Filippo, and Stefano Musacchio, in which we used the same model, but in the passive limit. Okay, the Eulerian model when a passive limit, so only one-way coupling. So if you want mass loading equal to 0. And this is for the two-dimensional chaotic flow, but we also studied the three-dimensional flow. And these are the two snapshots of the position of the particle advected by the full Lagrangian model, okay, for beta equals 0, this is the case of heavy particles, or from particles which are advected by the velocity field obtained by the Eulerian model. So you see that this is for Stokes 0.1, which is pretty small, but remember that this Stokes number is defined in terms of the Lyapunov exponent, because this is a chaotic flow. And so we know that the Lyapunov exponent is related to the Kolmogorov time to the factor 1.1. So in the turbulent case, it will correspond to Stokes, to the usual Stokes of order 1. So even with the Stokes of order 1, we have that the particle distribution is very close in the two cases. And also, to be more quantitative, what we compute here is the fractal dimension of the distribution of this particle in the two-dimensional plane as a function of the Stokes number. Okay, these are passive, so there is no mass loading. And the continuous line represents the full simulation, the Lagrangian simulation. So we know that at the beginning, Jeremy studied a lot this problem. At the beginning, we have a decrease of the particle density at the particle dimension because they cluster on this quasi one-dimensional line. But then you can go over 2 because the phase space has dimension 4 because you have both particle and particle velocity. And the points represent the result obtained from the Eulerian velocity. So this model, the Safman model, the passive Safman model, and you see that we have a quantitative agreement up to Stokes of order 0.1, more or less, which correspond to this snapshot. Then we have deviation because, of course, the particle cannot capture, the model, the Eulerian model cannot capture the fact that you have a multi-value velocity field. Okay, so this is really the end of my talk. Thank you very much. You can go to the conclusion. Okay, thank you.
Thanks a lot, Guido. So there is plenty of time for questions or comments or general discussions. So Ganesh raises the hand. Ganesh, go ahead.
Yeah, thank you, Massimo. Actually, I'm still trying to understand the first part of your talk. And so one question I had was, is there a physical mechanism? Is there an easy way to explain the result that you find of the changed region of instability in the plane? So is there a physical picture for the results from your multiple scales analysis in terms of why the particles destabilize the flow?
Okay, thank you. I think that at least I understand this part. Okay, so the limit of small Stokes, this can be understood because this is the general argument which was already raised by Safman. Then, as I mentioned here, sorry, I cannot go. It's very slow. Sorry. Okay, so this is the Safman model which we use for integrated simulation to make the computation. But if you take the limit of small tau, I already discussed it before. No, the limit of small tau, you can rewrite this model as a single equation. So is a Newtonian flow with a rescaled density, or if you want, we rescale kinematic viscosity and force. Okay, so now if you take this result as general result, and you go to the particular result of the stability of the Kolmogorov flow, okay, this expression where you take the limit of small Stokes, so you can neglect this term with respect to the others, and you recover this expression, which simply means that you rescale the viscosity by the factor 1 plus 5. And so the Reynolds number is scaled by this factor. This can be easily understood, this dependency. But the dependency on the Stokes number or the Stokes time, I don't have any simple explanation for this, which if you want is simpler in some sense because it's monotonic, but I have no a simple explanation for this.
Okay, so what I'm trying to think is that in the original model, so phi is the volume fraction, is that right?
The mass fraction.
This small phi there is the mass fraction there.
Yes.
Okay. Okay.
It's the same as the big phi before. Sorry. There's
but you had a phi m in the second part that denoted the mass fraction, or?
No, just at the beginning. I sorry, the notation is probably not full consistent. In the model, phi is the mass fraction. Okay. Okay. Just in the derivation, I discussed the fact that there is a volume fraction, but this is the mass fraction. Is the ratio of the density times the volume fraction.
Okay, I missed that. I thought it was the volume fraction.
No, sorry. It's the mass fraction because it's the momentum that injected the flow. So there is, okay, here there is a density missing here, no, as usual, but one over.
So the other thing that I was wondering was the Guazzoli-Morris's experiments were for pipe flow, right? And pipe flow is linearly stable, unlike the Kolmogorov flow that you found. And
Sure.
From what I have seen in later experiments is that the instability that they find seems to be qualitatively different and a supercritical sort of bifurcation as opposed to the subcritical instability that Newtonian pipe flow, that single phase pipe flow has. Whereas the thing that you find is just modifying the original supercritical instability of the particle-less Kolmogorov flow. Is that correct?
Yes, but this has nothing to do with, you are absolutely right. I mean, the stability, the pipe flow is linearly stable. So our results have nothing to do with the pipe flow. The mechanism is completely different. No, I mentioned just the result of Guazzelli because they found a similar behavior in a in a particle concentration. I'm not sure now if this is mass or volume concentration. Sorry, I don't remember. But they found that the flow becomes more unstable. Okay, the critical Reynolds decrease at slower concentration of particle and then increase again. So this is just the analogy between the two cases, but the two cases are completely different. I agree with you. The nature of the stability is different.
Thank you.
So thank you very much.